make up your mind about screen time after 3 o'clock on Monday, Tuesday, Wednesday. And on Saturday, please report. Because the second colloquium will not be held on Saturday, December 22. It will be done before. And the Saturday's classes will be cancelled. I don't want you to make colloquium after the Riviera part. So when you are free, on Monday, are you free at 3 o'clock? Are you free on Tuesday at 3 o'clock? Wednesday at 3 o'clock? Look at your looking in your table, and report on Saturday. Now, you have class on Tuesday, normal, no problem with the class. I mean only the Saturday. Today's topic, acids and bases. Before discussion of the theory of acids and bases, let us overview the equilibrium itself. Therefore, we shall be having a slight change in the timetable. The first paragraph from chapter 15 comes alongside with chapter 16, but 9 and 10 are removed for the time being. This will be next Saturday's homework. Not tomorrow's, but next Saturday's homework. Okay. Now let's discuss equilibrium and its constant. In a very rough approximation, we can discuss kinetic aspects of equilibrium. Kinetic equilibrium is kind of colloquial. With beta, we should be using something like quasi-stationary state. So equilibrium can be thermodynamic, and that corresponds to minimal free energy. We did not cover when we have equilibrium, the system has reached the minimal free energy. So free energy of the system cannot decrease any further. Then we can have stationary state. That means that no requirement is imposed on free energies. But stationary state means that there is no net change in the state. It doesn't depend on time evolution. There are processes running, but overall state does not change. If you take a chemical reaction, forward reaction and reverse reaction, then both reactions are running, right? But there is a moment when forward reaction cancels the results of the reverse reaction and vice versa. So we have equilibrium point. How and when and why this point is attained? Forward reaction rate depends on the concentrations of the reactants. If this reaction is being carried out, that means that the concentration of the reactants just decreases. Therefore, the rate of the forward reaction decreases. Initially, no reverse reaction is observed because there are zero concentrations for the products, right? But as a result of the forward reaction, the products are accumulated, their concentration increases, and so does the rate of the reverse reaction. Eventually, after some decrease in the forward rate and some increase in the reverse rate, they will balance each other. They become equal. So, then we are allowed to write equation, right? Forward reaction rate expressed by normal rate law equals the reverse reaction rate expressed again by normal rate law. Now, rate constants are constants, and any operation on those constants results in another constant. Therefore, simple transformation of the equation leads to the following formula, right? On the right hand, we have some fixed values for the concentrations. On the left side, we have the rate constants. And once both are constants at a given temperature, then we are allowed to introduce another symbol, capital K, and we shall call it equilibrium constant. What does it tell us? To consider the kinetic aspects of equilibrium, we just examined the portion. The value of K increases, as does the value of Kf, right? And decreases if the value of Kr increases. It's just a property of portion. If numerator increases, proportion, fraction increases. If denominator increases, then it decreases. Now, when it is high, when rate constant is high, in general, for forward reaction, we are allowed to write. And for reverse reaction, we again are allowed to write. That means that the higher the activation energy, the lower the rate constant is. This is normal Arrhenius equation. You learn it for tomorrow's class. Lower activation energy, the higher rate constant is. We have the opposite relationship here. If Kf is high, that means that activation energy for the forward reaction is low. If Kr is high, that means that activation energy for the reverse reaction is low. Now, this is high, this is low. When it happens, activation of the forward reaction is low, and activation energy of the reverse reaction is high. Now, let's just recall. How does activation energy relate to the stability? The higher the activation energy, the higher the stability. So if products are stable, then one requires substantial activation of the products. That means that the forward reaction will prevail. If reactants are stable and products are unstable, then the opposite is true. If these two values are more or less comparable, then we have practical case for equilibrium. Is this clear? So, if products are stable, then reverse reaction will be slow. Just look at it. If this has high value, then even small amount for reactants will be sufficient to give high reaction rate, right? By virtue of the multiplication. On the contrary, if this is low, then only high values for the products produce high reaction rates. In this case, equilibrium comes in effect when we have just traces, that is very small amounts of the reactant and very high amount of the product. Practically, this means that the reaction has been completed successfully. The opposite now. This is very low, this is very high. That means that the reaction will be balanced as soon as even small amount of product is produced. What does it mean? The equilibrium came in effect at the very beginning of the reaction. So for the practical purposes, we say that the reaction didn't start at all. Keep in mind, reaction ends only at the equilibrium point. The difference is when this equilibrium is attained. If at the very beginning, then we say that the reaction is impossible. If the very end, then we say that reaction was completed successfully. Otherwise, we consider practical equilibrium. That is, the rates become comparable when the product has not been fully exhausted. The reactants has not been fully exhausted and the product have not been fully formed. This is the case we have to consider in this lecture. Now, again, when we say equilibrium from the standpoint of thermodynamics, we actually mean stationary state for the reaction system, because there is no requirement imposed on the energy minimum. The third scenario will be so-called quasi-stationary state, which is the most advanced part, which is really required for life sciences. You will learn it in biochemistry, hopefully. Quasi-stationary state means that you remember stationary state means no net change, right? Quasi-stationary state means very slow change, but there is a change. Example, life. There is a slow change, but life eventually terminates, right? Whatever happens, we have sinization process. Do you understand what is sinization? Becoming older, right? This is a chemical process. So life is a quasi-stationary state, and it requires special mathematical apparatus for description. A complicated apparatus. You should be interested in this issue whenever you have a free time, because it gives lots of insight about metabolic transformations. Now sum up. Equilibrium is the result of balancing reaction rates. We do not say anything about the internal energies and free energies of the reaction system. We discuss practical equilibrium points. This is when reactants are not fully exhausted and products are not fully formed. K, the equilibrium constant, gives us an idea when the equilibrium comes in effect. For very high values of K, at the very end. For very low values of K, at the very beginning. In between, we have practical equilibrium. Is this clear? Okay. At the next lecture, we shall consider another device, so-called reaction quotient. And then we have a numerical comparison between the current state and equilibrium. But right now, to discuss acid-base theory, we do not quite need reaction quotient, so directly let us go to the acid-base theories. So some compounds are referred to acids, some compounds are referred to bases, and it is well known that in water, the common definition for an acid is an electrolyte which releases proton, and base is an electrolyte which releases OH-, hydroxide ion. This is a useful definition. Why is it useful? Just because it describes acid-base transformations of water solutions. But it is a limited theory in the sense that water is not the only polar solvent. And to have a general idea about acid-base reactions, we need to consider scenarios when we have non-polar solvent, first of all, and no solvent at all. But let's do it step by step. Let's extend this theory to the case when we have polar solvent. This is so-called protolytic theory, Bredsted-Lowry theory. What is the rationale behind this? Classical example will be, everybody knows, even from the daily practice, that solution of hydrocarbonate ion has basic reaction. Why is this a basic reaction? Because we have transformation like this, right? Then it is decomposed. And eventually here, CO2 is released, right? So, now let's discuss this reaction. This thing does not have OH, but still we have OH released, right? That cannot be described by the Arrhenius theory. So, what is modified here? The definition for bases are modified. Base is a substance which accepts proton. Acid again is a substance that releases proton. And base is a substance which accepts proton. Now, look. This accepts proton from water. One proton extra, right? And proton is missing from water. The general thing will be, we still consider water solutions, right? Then we go to other polar solutions. No. Why do we write hydronium? due to ion dipole interactions. H plus water, H plus water will be hydrogen. There are strong ion dipole interactions, right? So protons actually are not free, they are bound to water molecules in the water solutions. We still extend the definition of acids and bases by the concept of conjugate acids and conjugate bases. So, now let's examine the scenario, right? We take this, and from this we get this. Proton is 4. Now, if this is a monoprotic acid, you probably know what is monoprotic acid, right? Only one proton can be released. It cannot release proton anymore, right? It can only accept. Therefore, by definition, this should be a base. And this is acid, right? But they are conjugated. Such pairs are referred to as conjugate base to the acid. So this is acid, and A- will be the conjugate base of the aforementioned acid. Now, this one, accepted proton, right? So we have base. Can hydronium ion accept more protons? It cannot. It can only release protons now, right? Therefore, it should be acid now. And we have conjugate acid for this base. So what is a conjugate base? You take acid, remove one positive charge, one hydrogen. Whatever remains will be the conjugate acid, base of the acid. What is conjugate acid of the base? You take the base, add one positive charge and one hydrogen, right? Whatever is produced will be the conjugate acid. So this thing should be conjugate acid for this base. We added one positive charge and it becomes neutral, and one hydrogen, right? So one more hydrogen, one more charge. This is conjugate acid for this base. Now this acts like acid. It releases proton. Whatever remains will be its conjugate base. Sometimes, you surely know this, we have compounds which do even. Water is an example, right? Here I got proton, here I donated proton. So here it acts like acid, here it acts like base. Such things are referred to as ampholytic compounds, ampholytic acids or bases, or zweiterions. Zweiterions are a special case, and we better consider them when we discuss amino acids. This is also ampholytic thing, right? It has one more proton, so it can release this proton. Water and water, right? Now, here it is acid in this reaction. In this reaction, this will be base. What about this? It is a conjugate base of this acid, right? So in the reverse reaction, this will be base and this will be acid. The strengths of acids and bases, conjugate bases, relate to each another. The stronger the acid, the weaker its conjugate base is. So let's take HCl and we get Cl minus, right? This will be its conjugate base. This is a strong acid, so what can be said about this base? Should be very weak base. Now, let's take HF. This is a weak, right? Therefore, it should be a stronger base than this thing here. Or even better example, NO2 minus and proton, right? Let's keep water right now. Weak acid should be not so weak gas. The case when we have a relatively weak acid and we get relatively weak base anyway is useful for the description of the hydrogen bond. You might remember that we do not have exact potentials for hydrogen bonding. Still, we need a device, a tool to estimate the strength of hydrogen bond. So usually, let's consider this thing. neutralization in terms of the Brensted-Lowry theory should be the process of the proton transfer. Proton is transferred from acid to base, right? So for establishment of a hydrogen bond, we need a proton donor and proton acceptor. But they must be of comparable strength. What happens then will be the following. Proton does not fully depart from the acid and does not fully seat on the base. Therefore, hydrogen bond formation will be partial neutralization process. Is this clear? Okay. How can we tell whether acid is strong? You remember, look at the definition for the equilibrium constant. If acid is strong, how can we judge about the strength? First of all, we must numerically measure the concentration of hydroniums in water solution, right? If there are more hydroniums, that means that reaction enters the equilibrium point at the end, when reactants are almost fully exhausted and products are almost fully formed. So this says that Kf should be far larger than Kr. Now look at the Arrhenius equation. Kr is small value when activation energy is high. But if activation energy is high, that means that something is stable there. So how can we tell whether acid is strong or weak? We remove proton. So one hydrogen and one positive charge. And look at the remaining thing, which is conjugate base. If the conjugate base can stabilize itself without regaining proton, then the acid is strong. If the conjugate base can stabilize itself, that means that the process of proton acquisition will be accompanied with high activation, right? If there is high activation, then there is high stability. So how can we tell, again, that a compound is strong acid? Remove proton and look at the remainder. If the remainder is stable, then you have strong acid. If the remainder is less stable, then you have weak acid. The same is true about the bases. Put H plus on the base and look what is produced there. If the excess of the positive charge can be dealt with by the structural phenomena, by redistribution of the electron density, then we have strong base. Otherwise, we have a weak base. So, the criterion will be stability of the conjugate entity. For acids, stability of the conjugate base. For bases, stability of the conjugate acid. Is this clear? Okay. Then, let's start slowly numerical analysis of the acidity of the solution in question. As a model system, we have to consider pure water without any additions, right? First of all, for practical purposes, we still consider water solutions. So we need to know how is made the change in the concentration of protons in the water solution. To understand what is the change, we must first take a look on what is in the beginning, before the change happens. This is a normal reaction. Water plus water, hydronium plus hydroxide. What can you say about the reaction rate? The forward reaction is a bimolecular process, but the rate is pseudo-zero. Why is this? Experiment shows that when we measure concentration of hydronium, it will be 10⁻⁷ moles per liter. And then the stoichiometry suggests that to produce one proton, only 2 molecules out of 10 million need to react. So 10 million minus 2 is actually 10 million again, right? The change is minor. Therefore, when we consider forward reaction, we have to ignore the change in concentration of water. And this suggests the following expression for the equilibrium constant. Denominator has to vanish. There is no change there. We have concentration of hydroxide times concentration of hydronium, and for any compound, this product is protons times conjugate phase will be constant. For water it is 10 minus 14. We call this water ionization constant. So, if we increase the concentration of protons, then the concentration of hydroxides decrease, and if we increase the concentration of the hydroxides, then the concentration of the protons decreases. Once we have small amount of protons there, then with better change numerical value, rewrite it. Therefore, we take logarithm of actual concentration to work more conveniently with the proton concentrations in water. Sign minus is changed and the remainder is referred to as pH. For pure water, then pH equals 7. This is the situation which is commonly referred to as neutral medium. Keep in mind, high pH means low concentration for H's, because we have taken minus logarithm, not the direct logarithm. Low pH therefore means higher concentration for protons. The more protons, the more acidic the medium is. Therefore, from pH 0 to pH 7 we have acidic medium, strong acidic first, weak acid next, then we have neutral point, pH 7, then we have basic medium, weakly basic first and strongly basic next. One thing is here, we have to keep in mind the difference between basicity of the solution and alkalinity of the solution. Basicity is given by the concentration of protons or the corresponding equivalent of OH minus. Alkalinity, however, is given by the concentration of protons, which is required to neutralize excess of OH minus. These are different things because input of extra H plus can trigger some other processes. Therefore, either less can be required or more can be required for complete neutralization. pH is a widely established numerical measure. For acidity, nowadays you might see another measure. This is concentration of protons divided by the concentration of their conjugate. For water, it will be concentration of protons divided by concentration of hydroxide. When you take normal logarithm without minus, then we have the following situation. Suppose concentration of protons is 10 minus 3. Then this will be acidic, right? Concentration of hydroniums correspondingly will be 10 minus 11, right? Because 3 plus 11 should be 14. 10 minus 3 divided by 10 minus 11 will be 10 minus no, plus 8. So, logarithm from plus 8, 10 plus 8 will be 8, right? Acidic. Now, take another case. 10 minus 5, briefly acidic. 10 minus 7, right? The division yields 2 now. So, as this value increases, so does the acidity. There is no opposite correlation like in pH. And if it becomes negative, then we have basic solution. If you see expression like this instead of pH, don't be surprised. This is a more convenient numerical measure for acidity of the solutions. Is this clear? So what is pH? It's just the logarithm of concentration of protons, the negative of the logarithm of the concentration of protons. formal definitions for strong acids and strong bases will be the following. For the practical purposes, we assume that acids are strong if they are electrolytes and if they decompose fully. So, discuss the previous thing. HBr is a strong acid. And initially, we have, let's say, some moles of this concentration, right? Final concentration, however, will be 0. Let's consider strong acid and weak acid here. We can derive some methods for dealing with pH there. Strong acid plus water, we have, no, we derive only forward arrow, not the reverse arrow, because we ignore the reverse reaction. Initial concentration is Cm, and for those initial concentrations are expected to be 0. If the final concentration is 0, then we say that we have a strong acid. Then the stoichiometry suggests that concentration of hydronium should be numerically the same as was initial concentration of the acid. So pH of strong acid then depends on the concentration of the acid taken. Now what about weak acid? For the weak acid we cannot be sure that the acid has been fully ionized, right? So let's say that we have X moles for hydronium. Then by stoichiometry we shall be having X moles for the conjugate base. And what will be the equilibrium concentration? Initial minus whatever weight, right? The equilibrium constant should be written then concentration of this times concentration of this X squared by concentration of this. We again ignore changing concentration of water. Now, most often, for practical purposes, it is safe to assume that this approximation holds. If acid is really weak, then its loss can be ignored. In that case, we have x is the square root from this expression. Right? X is going here, here we have only Cm, then multiply by Cm and take the square root. But we need to check the approximation about the validity, right? Against the validity. This should be 5% of the initial concentration, or less. If the outcome shows that X is more than 5% of the initial concentration, then this approximation becomes invalid. Therefore, we return to the original equation, then we have to solve quadratic equation by very normal means. We just calculate discriminant and then do like it is suggested by the normal school textbook formula. But again, most often we do not need to solve quadratic equation. All we need to do is take the Ka, multiply it by the concentration and take the square root. It will not show pH, of course, right? It shows just the concentration of protons. Then we must take the negative of the logarithm. The above is an example of strong acid. The bottom equation suggests weak acid bed. Is this clear? Then one more equation. We do not need this equation in this chapter, but it suggests physical meaning for pKa and Ka. Logarithm is 0 when this thing is unit, right? This thing is unit when the acid is exactly half dissociated. If it is 0, then we have pH equals pKa. So the physical meaning for pKa will be pH at the point of half dissociation of the original acid. The equation is Henderson-Hasselbalch equation, which is required for modeling buffer systems. We are going to discuss buffers at the next lecture. Is this clear? Okay. Now, let's consider the case where we do not have solvent, for example, or we have no polar solvent. We mentioned that neutralization reaction is a proton transfer reaction, right? Proton leaves acid, and goes to the base. It's just like redox reaction, when electrons leave something and go to another. The idea is, can we discuss acid-base reactions in terms of electron motion, not in terms of proton transportation? The Lewis theory suggests the following thing. Acid is something which has vacant orbitals. Base is something which can donate lone pair. For example, if we take the third group elements, they have incomplete octet, right? Therefore, they are natural Lewis acids. If we take the fifth group compounds, nitrogen, phosphorus, they have expressed lone pair. Therefore, they are Lewis acids. If you are confused, take proton. Proton is acid, right? It must stay acid in any theory. Proton has no electrons. It has only vacant orbital, right? Therefore, recalling, proton is acid, it has vacant orbital. Let's say that everything which has vacant orbital will be acid. Now let's discuss practical examples of neutralization in terms of Bronsted-Lowry theory and in terms of the Lewis theory. It is well known from organic chemistry that aromatic compounds, benzenoids, can undergo only electrophilic substitution reaction. So we need a positively charged particle to get substituted in the benzene ring. Therefore, if we want to substitute nitro group, we need to produce NO2 plus. It is a difficult process. How it is produced? We take concentrated nitric acid and concentrated sulfuric acid. What we have will be and plus here. How do we know this? This is a stronger acid than this. Now, sulfuric acid removes water from here, and we have NO2 plus water. And this gets substituted. This is a practical reaction used for nitration of benzene rings. The same is true about halogenation. We need to produce chlorine plus. Not chloride minus chloride, but chlorine minus. Again, it is difficult to produce. Then we use Lewis acid and something like this. What will be the outcome? Lone pair, even bonding lone pair, comes to the vacant orbital, and we have now aluminum Cl4 has negative charge and chlor has positive charge. Then this thing can be substituted into the benzene ring. So this is base because it holds proton. This is acid because it gives away proton. This will be the conjugate acid and base. This is base because it gives electron pair. This is acid because it gets electron pair. The result will be so-called Lewis salt. Is this clear? So, to sum up, Lewis bases discuss acid-base transformations without the help of protons. They are valid for aprotic compounds, that is, compounds having no proton to release at all. Lewis acid is defined as an entity which has vacant orbital to host lone pair. And Lewis base is defined as a chemical entity which can share its lone pair. The process of lone pair transfer is referred to Lewis neutralization. It is very important if you have intention to learn organic chemistry, not just to memorize organic chemistry reactions. Without understanding which is Lewis base and Lewis acid, there is very difficult to understand the mechanisms of the chemical reactions. And without understanding the mechanisms of the chemical reactions, the only remedy to such a student will be to memorize the reactions. It is difficult to memorize 50 reactions when they have one mechanism. Understand mechanism, you remember just the mechanism and apply it to different reactions. If you don't understand the mechanism, to you then all reactions will be different. And then you will have to memorize this. Therefore, pay particular attention to Lewis theory. Bronsted-Lowry theory is a very good thing for understanding hydrogen transfers, proton transfer processes. Lewis theory is helpful to understand the mechanism of chemical reaction and the action of catalyst in organic reaction. So, essentially that's all. This is not quite required. We discussed this slide, right? Conjugation basis can be calculated. And now, the small portion. We have two common mineral acids. The first class is we do not have oxygen. The second class, we do have oxygen. As a model system, we just described hydrohalic acids, right? Why HF is a weak acid? The difference in electronegativities between hydrogen and fluoride is huge, 1.9. HF actually is a unique compound. It's covalent compound and ionic compound at once. Why? Due to high polarization of HF bond, the partial charges become as efficient as full charges. Therefore, HF bond is the result of interaction of lone pair, which is shared, and purely electrostatic interaction. And decomposition of HF becomes difficult. It requires high activation, and for the rest, acidity increases. Iodine has greatest radius, right? Therefore, removal of proton is simply easy, just due to electrostatic forces. Now, oxoacids. It is easy to compare the simplest cases. The first case, same oxidation state of the central atom, but different varieties. Then acidity decreases from top to bottom. HClO3 will be a stronger acid than H2O3. And the second case, the same element but in different oxidation states. High oxidation state usually means high electronegativity. Therefore, the greater the oxidation state, the stronger the acid is. HClO4 will be a stronger acid than HClO3, then O2, then O. Okay? So, to sum up, hydrohalic, non-oxygen containing acid. We look at the electronegativity of the atom which releases proton. And we consider bond strength. For oxoacids, we consider two things. The same oxidation state, different element. Above, stronger. But we don't have oxofluoroacids, right? It's impossible. The same element, different oxidation states. The greater the oxidation state, the stronger the acid is. Okay, that's it. Final note about the homework.